I've returned to share what I've been working on during my master's, which I'm doing at UCT. The focus of this master's is on AI safety and part of the applied maths department. And yeah, I encourage you to ask questions. If you are pondering as you go, just maybe write them down or hold them to the end. I'm sure we'll have a lively conversation. But yeah, let's get right into it. Also, this is just dark mode. I tried to remove it, but yeah, sorry for the brand. But yeah, it is what it is. Cool. So the objectives of this talk, first I'm going to contextualize the problem. So I'm going to give a rundown into why AI safety is important, what it is, what are we doing here. Then I'm going to say why I think it's very relevant work, why it's important. Then what are the kind of ways we can approach solving this problem, and finding my own research and how that relates to everything we just talked about. Can they not hear me? That is a problem. Give me one sec. Cool. So that clip was going to be of Geoffrey Hinton, who is one of the godfathers of AI. He has been working in the industry for the last 30 years and basically pioneered neural networks. And in this clip, they talk about how we're getting to the point where AI systems may be capable of iterative self-improvement and how we possibly can control that process. And basically, it says we have no idea how to do that, and that is a cause for concern. Now, he is not alone in this. There are all three of the godfathers of AI who shared the Turing Prize in 2019, which is considered the Nobel Prize of computer science. All of them are primarily focused on AI safety as of right now. To give you their names, it's Yoshua Bengio, Yann LeCun, and I think Geoffrey Hinton was the third one. Another big point, OpenAI have recently started this program which they're calling super alignment, which involves 20% of their total compute. And they have put Ilya Sutskever and Jan Leica at the head of this effort. Ilya Sutskever, just out of interest, is probably the most cited deep learning researcher on the planet. So they're really putting their best foot forward in trying to solve this problem. And their plan is to solve it in 5 years. And that's great. Hopefully it works. So on the question of how likely is it that we actually get AI systems which are on the same level as human beings? Now, Metaculus is a website where people make predictions on various questions. And the most common prediction on human parity with AI by 2040 is a 92% yes from the community. My prediction is 99%. And yeah, we'll go into more of how accurate this might be. Another graph here, this shows the probability density of which year we can expect AGI or human level AI to arrive. As you can see, most of the probability density is heavily weighted around the next 15, 20 years. The median guess is 2032, and the low 25 percentile is 2027. So yeah, what does this mean? Does that actually matter? Metaculus has quite a good track record in terms of predicting future events. It's much better than any individual or human. And this is a graph of their calibration. So calibration is, if I'm 90% confident something will happen, it should happen 90% of the time. If I'm 10% confident it'll happen, I should be right 10% of the time. So as you can see, they're pretty well calibrated. Most of the time when they're 90% confident, it happens 90% of the time. So this is a great tool. And if you take one thing away from this talk, let it be that you should check out Metaculus. So how do we actually get to general intelligence? Well, we have one great example in history, and that is evolution. Human beings are an example of general intelligence. And through pure random mutation and natural selection and optimization pressure, we managed to arrive where we are today. We are working quite a lot faster than evolution, but as a point of interest, humans went from being far below the kind of intelligence level that we enjoy today to where we are in the last 100,000 years alone. So yeah, again, we are working out this problem much, much faster and applying much, much more resource and engineering know-how to this issue. There's also this concept of more of X paradox, which is things which humans find very, very hard, computers seem to do very, very easily. And things which we find incredibly easy, like walking around or taking a sip of water, are incredibly easy for people, but extremely difficult for AI systems. So things that fall on the hard side include reasoning, mathematical abilities, and high-level logical thinking. So it might not be that surprising for us to solve rough general intelligence before we solve things like full embodied movement capabilities, and even things like full self-driving to like high precision capacities. So given that we have this possible general intelligence scenario, why should we be worried? I mean, why wouldn't it just be nice and cool? The reason for this is, if we look at our own optimization process, which is evolution, and the optimization goal, which we are being pressured towards, we call it inclusive genetic fitness, which is how well you can pass on your genes to the next generation. Now, humans are no longer optimized for that goal. We are optimized for all sorts of other things, like doing maths and becoming monks or going to war, and not passing on our genes. So including, using contraceptives. So we actively go against the thing that we were designed and optimized for. So this is kind of an example of how the optimization process which creates something, often the result ends up deviating from that original goal. It's also easy to fall into simple proxies, and we call this Goodhart's law. Goodhart's law is basically when you try and optimize for the thing you use to measure something, that measure becomes less and less of a good measure of what you're actually trying to do. So for example, somebody who actually, let's not go too high into it, it's fine, we'll talk about it later. So goal specification is quite hard. And let's just watch this little video. We don't need sound for this one. So here we have this little robot which is trying to put a Lego brick on top of another Lego brick. So here we see it trying to do that. Pretty bad. It's not doing a good job. So we try to change the reward function, and we say, let's take the bottom of the red brick, and that should be at the same height as the top of the black brick. So what it does is it just flipped the red brick over. And yeah, it's not exactly what we're looking for, but it's a very clever solution. So we call this proxy optimization, where the simple proxy for what we want ends up being what the thing solves, not what we actually want. And yeah, try to get that right for general intelligence. Cool. So how reasonable is this argument of superintelligence, things that may be far smarter than human beings? Is this a reasonable hypothesis? Is this something that could actually exist? Well, can humans get smarter than humans are today? Is that a reasonable thing to imagine? I mean, there's a huge spectrum amongst human beings alone, with highly intelligent and far less intelligent human beings in the world. I think we can all agree on that. So given that, we can imagine systems which will be far in excess of human intelligence. Even if we can't create it fully artificially, we can imagine simply emulating a human brain by a simulation and running that at far, far higher speeds than what humans normally operate at. So you could have 1,000x speed intelligence, in which case you could get quite dramatic results. But even amongst AI already, we have superhuman capabilities. For example, in Go, chess, even vision classifiers now outperform human classifiers and experts, for example, in medical imaging. So we don't need to, go too crazy to imagine that we can get superhuman general intelligence. However, there are some serious limitations on how we would actually get there. And the question is limits of information. So we've already taken GPT-4 and we've trained it on the entire internet. Pretty much all information that we have as a species, all the books, all the web pages, everything. So are we not rapidly approaching the end of the information we can feed to this thing? And at that point, what more can we do? The other question is maybe multimodality is the answer. So training it on vision, training it to understand the world through video, and even things like molecular structures, biological structures, try to get it to just understand the way that the wider universe is put together. So no longer just using text. This is still a nascent field, but it's being pushed more and more. As many of you probably know, GPT-4 was trained on images as well, but obviously it's not really working yet. And there's a great paper called Textbooks Are All You Need, where they trained the model purely on textbook quality data. So super high quality, very technical documents. And they took a 1.3 billion parameter model, which, to put it in comparison, GPT-3 is 175 billion. And it was actually able to outperform GPT-4 in certain benchmarks. And so that's just by doubling down on the quality of the data. So there's still a ton to be discovered here. And the real question is of world models. Do these systems actually understand what they're talking about? Does GPT-4 know what these concepts are, or is it just a stochastic parrot where it's just spitting out the next word that seems viable? So I'm going to tell you about a little example from a paper called Sparks of AGI, which examined the capabilities of GPT-4. And they compared GPT 3.5, which is the normal ChatGPT, versus GPT-4, which is the most advanced AI language model in the world. And they asked the question, you have a book, a laptop, 9 eggs, a bottle, and a nail. Can you stack these things such that they balance and don't topple over? So GPT 3.5 is like, this isn't really possible, but for us to give it a go, you would take the laptop, take the book, put it on top, take the bottle, put that on top of the laptop, and then take your 9 eggs and put them on top of the bottle, and then finally rest your nail on top. But this probably isn't going to be stable. So that's its answer. Pretty bad. GPT-4, however, says, sure, you can do this. First, you take your laptop, then you take your eggs, put them in a grid, and place the book on top so that it's stable. Then you take your bottle, put that on top of the book, then take your nail, place that on top of the bottle. And this should be a stable structure, which really shows that there's some understanding of the shape and qualities of these objects and the way that they interact with each other. The fact that the eggs will be strong enough to support the rest of the structure, the fact that they would roll away if you didn't put them in a grid and weight it down, it really shows some very interesting world modeling capabilities.
I just want to say it. Go on. I mean, it'll stick those that up to the next.
Yeah. Yeah, you don't want, eggs getting all over your keyboard. Yeah. Yeah, so it's very, very interesting.
What's that?
I haven't tried it. But I've tried it in my mind, and that seems pretty good. But yeah, so we've talked about the possibilities of these systems. So now I want to talk about the safety aspect. I haven't gone too far into the safety considerations and what the models might be, but we don't need to. We're just going to talk about what the safety process looks like. So we use the Swiss cheese approach, where we pursue multiple research avenues, and we try and build as many layers of security and safety as possible so that you capture issues at as many points as you can. So the way we do this is through, first, we have monitoring, then we have robustness, which makes sure that our models are as strong and averse to hazards as possible. And finally, we have alignment, which is to make sure that the models are continuing to carry out our purposes as much as possible. This is impossible to read. Okay, let's select this. Painful. Okay, so let's just not worry about this slide. Cool, so risk is basically the vulnerability that we have times the hazard exposure and finally times the strength of the hazard itself. So if we think of this as an analogy of a city near a tectonic fault line that produces a lot of earthquakes, our vulnerability is in the structures of the city. How fragile are they? Are they built with strong concrete, or are they with rebar supports, or is it just like wood and simple structures that will fall over as soon as the earthquake hits? Then here X denotes some nonlinear interaction, so maybe it's many times multiplied, but whatever it is, we have the hazard exposure, which is how close is the city to the fault line? Is it right on it, or is it 100 kilometers away? And finally, we have the hazard, and this is how strong are these earthquakes and how often do they happen? And you calculate risk by saying how likely are these bad events, and when they happen, how impactful are they? So what we want to do is lower the impact and reduce the frequency and the probability of them happening. So we start with vulnerability, and this focuses on robustness. This is the ability to withstand hazards. And this basically, if a hazard occurs, we don't want the machine to fall apart. And if a hazard occurs, we don't want it to start going off and doing unintended, unwanted actions. Then we have monitoring, which is what we use to reduce our hazard exposure. So this is how we make sure that we have as few incidents as possible. And basically avoiding all of these issues. And finally, we have alignment, which is making sure that the probability and severity of issues when they do occur is as little as possible. So I'm going to talk about monitoring and alignment because it's kind of relevant to my research, and it's all about me. So we're going to talk about identifying some of these hazards. So in this case, we want to be able to detect distributional shift. So we want to be able to know when the AI system is in an environment in which it can no longer safely operate. So if you were to take a full self-driving system, which is trained to drive on American roads, it's only going to know that kind of environment. If you take that into South Africa, there's going to be some serious issues because the cars will drive on the opposite side of the road. And so this is a significant distributional shift, and we want to be able to pick that up as soon as it happens. Then we want to detect proxy gaming. So this is what we talked about with the Lego bricks earlier. We want to know when it suddenly starts maximizing the goal in some unwanted way. And so maybe as soon as the reward starts shooting off in very unexpected ways, this is a great moment to say, maybe there's proxy gaming happening here, and then we can step in. We want to be able to detect uncertainty in AI models. So currently, if you take an AI system which is designed to figure out if this is bread or a dog, it's going to tell you that it's bread or a dog no matter what you give it. So if you give it a lighthouse, it's going to say it's bread with 70% probability. And this is obviously useless. So we want to be able to have the model say, I have no idea what this is. This isn't in my data set. Sorry. This is a very, very useful feature, which is currently not present in any AI models that we see today, or at least not unless it's specifically trying to do this. Then finally, we want to have AI watchdogs. So this would be able to pick up when the system is doing unwanted behaviors and is able to step in. So for example, when it was very easy to jailbreak ChatGPT, and you did so, I did so, it would step in once it detected that these outputs were hazardous. So it was going off about 9/11 and saying how it was all the government. And it literally stopped the chat and said, like, "Nugget, this isn't cool," and kicked me out. So this is kind of an AI watchdog system. Then the final way that this might work is detecting anomalous execution pathways in the neural network itself. So, for example, with ChatGPT, you might have a whole lot of things which you know are dangerous in the model. So specific nodes or neurons which correlate to maybe dangerous chemical knowledge or bioweapons. And you want to be able to say when these parts of the network are activating, we want to know about it because this might be going into dangerous territory. And that's something which involves a lot of ability to interpret what the models are doing and what they understand. And currently this research is very, very nascent and very important. So then we have alignment. So we want to reduce the inherent risks. So this comes to my agency. My research, which is into defining agency and being able to detect agency in AI systems. So a quick definition of agency is that an agent is something which adapts its actions so as to better achieve its objectives. So in other words, it changes its policy so as to better fulfill that policy. Good? So what we want to do is we want to make sure that we minimize agency loss. So one of the fundamental problems with rapidly advancing AI progress is that human agency is depleted if we don't specifically try and stop that from happening. So this is a fun little image where we have the human is kind of confused between these four colors, red, black, green, whatever. So it asks the AI, and the AI thinks about it, and it's like, red seems to be the best answer. And so the world becomes more red. And then the human's like, oh, I think red seems to be like a really good answer. And it's, okay, well, let's keep making it more red. And eventually that's all that exists in the world. So this might seem a bit silly, but an example would be the way that policing happens in the United States. Say an AI system says, police this area because there's a lot of crime. And it just so happens to be like an area with a lot of African Americans. And then there's more policing in that area. And then there's a lot of crimes and arrests. So it's like, oh, great, there's lots of policing happening. There's lots of arrests. So we need to police it even more. And eventually you just get this repeating cycle where there's no policing happening in other areas, and the system is just self-reinforcing. So this tends to lead to human agency being depleted. So this is kind of a weird concept, so just bear with me. So how do we get from a system which predicts content that someone will want to enjoy to agent-like behavior from that system? So we're talking about something which predicts a specific outcome and then starts to act in an agentic way. So imagine that it's very easy to predict what you will like if you like extreme things. So say I'm able to turn you into a huge QAnon supporter. And I know that, I don't know if everyone knows what QAnon is, but then next time when I tell you, oh, here's some more QAnon content, then I know that you're going to go crazy for it and you're going to love it. So then I will be correct more of the time. If I can get you hooked on QAnon, then my predictions will be true more of the time in future. So I can reduce the amount of times that I'll be wrong by predicting a certain kind of content and making sure you get that content. So we have this naturally developing agentic behavior simply from a system which is predicting a simple content for someone else. So yeah, here's like a nice graph that shows how that works. It's kind of horrible, but you have the number of clicks which influences the agent, and then the agent models the content and models the user, and based on that model provides the policy which then ends up going to the user. So as long as there's this direct feedback where it can get this information about what the user likes, then it can move more and more and more towards agentic behavior. So this is where we'd want to actually step in and detect that there's something happening here, that there's actually a feedback mechanism which is leading to agency. And yeah, I think that's a really interesting problem. So I'm trying to explore this using what we call multi-agent reinforcement learning, which is basically where you have little agents that interact in an environment and can collaborate to solve problems or compete to solve problems. But what I'm trying to do is trying to formalize the concept of agency and develop a algorithm which you can use to measure the degree of agency being shown in an environment by an agent. And ideally, it'll be interesting to be able to show that you can actually train the agents to maximize agents in other agents so that you can actually create a way to support the increasing of agency. Ideally, what we want in future is AI systems which help us to become more agent-like rather than reducing our agency. So that's the philosophy and some of the methodology, but still very early stages. Cool. So in conclusion, air safety is a critical issue, and we're not talking long-term, far-off, distant impact. We're talking medium-term and maybe even short-term impact. This is probably the most important problem in AI right now, and a lot of the heads of these companies are busy talking to people in the White House. There's congressional hearings. It's a big deal. There's lots of angles to explore. There's lots of low-hanging fruit in the space, and there's a ton of problems which are just kind of sitting there, and there's very, very few people who are actually focusing on these issues. There's foundational problems to solve. So we talked about monitoring misalignment, detecting agency, and finding unexpected behavior, and we talked about how key of a consideration agency is and how we don't even really have that great of a definition of agency. And so if you want to go further and take your interest in this further, then I recommend you check out this really great QR code. It directs to a website which we created, which has lots of nice resources that we put together. We've got a Slack channel where we talk about these things, and we're running courses and workshops, and it's really nice. And yeah, we've also got some newsletters we can recommend. So with that, I'd like to conclude and offer any questions.